the second part of the Chapter 13 homework deals with density and fluid flow. These in particular deal a little more with fluid flow. And so there's 1, 2, 3, 4, 5 problems with this. So the first part here, problem 35, you've got a pipe 1 centimeter in diameter, 2 centimeter in diameter, and then 0.5 centimeter in diameter. And it tells you the velocity here. And then you're asked to find the velocity at this spot and at this spot. So the speed is inversely proportional to cross-sectional area because we've got this continuity equation here, which is area times velocity equals our volume flow rate. So I ended up figuring out the volume flow rate first, which was actually question B. So the velocity was 4 meters per second here, and pi r squared. Well, the radius of this would be half a centimeter, which is 0.005 meters. So pi times 0.005 meters squared gives me basically pi, or 3.14 times 10 to the negative fourth cubic meters per second, and that's our flow rate. That would have to be the same through these other two regions as well. Since this is a wider part of the pipe and this is a narrower part of the pipe, it's going to be going slower through here, faster through here. So at 2 centimeter diameter, the cross-sectional area is 4 times as much because the area of the circle is pi r squared. So if I have 4 times the area here, then I would have 1/4 the speed using this formula. So I can proportionally figure out that this is 1 meter per second without actually going and doing the whole calculation. The same way here, if this is 0.5 centimeters diameter, that means the cross-sectional area is going to be 1/4 that of what we had initially over here. And so therefore the speed would have to be 4 times as much. So that would be 16 meters per second. Problem 37 is a Bernoulli problem. I think this shows why it looks very intimidating, but it does not have to be super complicated. So you're given that a pressure down here was 200,000 pascals, speed down here, speed up here, 10-meter height to get it up to the top, and you were told it was oil. So from table 13.1 in the chapter, we can figure out that we've got 900 kilograms per cubic meter is the density. So pressure 1, pressure 2, we're trying to find pressure 2, which is here at this. And these are not open to the air, by the way, it's just my drawing. So pressure 1 was 200,000 pascals. If this is the bottom, we think of our H as being 0. So then it's 1/2 rho v squared. And then that would equal at the top the pressure here plus rho gh, and that's a 10-meter height, plus 1/2 rho v squared there. So we were given the speeds at both these locations, which makes this pretty easy to figure out. So the pressure at 2 is 109,600 pascals. So it's a bit less here than it is here. Kind of makes sense because it's going faster. For problem 39, this is similar to one of the questions I think it was Jarrett asked in class about the FET simulations. So basically, if we have something coming out here, we've got a surface up here. If we have a 2 meter long, 0.6 meters wide, 0.45 meter deep trough, there's a small hole at the bottom edge. What speed does it leave the trough? This is something called Torricelli's theorem, and it basically says if both these are open to the air, the pressure on each side is the atmospheric pressure, so that's the same, so that cancels out. If this is a very large area compared to this, then we have a very slow motion, which approaches 0 meters per second, that this would be draining. So that cancels out to be in a 0. And at point 2 here, if this is at the bottom, we would think of our height 2 as 0. So we have rho g h1 equals 1/2 rho v2 squared. So that cancels out a lot of terms of that Bernoulli's equation. And we're getting around 2.97 meters per second. And notice, although it said this was water, the specific density doesn't matter. As long as the density is the same, numbers would give you the same speed. Problem 40 was a little bit sneaky, I thought, because you had one pipe and it's splitting into two pipes. And this pipe is 3 centimeter diameter. This one's 1 centimeter diameter, 1 centimeter diameter. And we're looking at points A and B. You were told that the pressure was 50,000 pascals at A, and you were told it was a gauge pressure, but you were asked to find a gauge pressure. So at that point, that's all we know. So I don't think we have to use absolute pressure like we normally would think about. That still concerns me a little bit. At any rate, we can find out the volume flow rate at 1 here. So the area is pi r squared. This is 1.5 centimeters, or 0.015 meters is the radius. And then we multiply that by the speed there. And that gets me my volume flow rate of 1.414 times 10 to the negative third cubic meters per second. That total flow is going through both of these pipes. So that's why I'm writing this as essentially, well, it doesn't like that. This volume flow rate is equal to 2A2 times V2, because I've got two pipes. Each of them is going to have the same area because it's got the same diameter, and therefore each is going to have the same velocity. So when I do that, set it equal to 2 pi r squared again, 0.005 squared times pi times V2, I end up getting that each pipe here is going 9 meters per second. So significantly faster than what was up here. But if it was a 1 centimeter, if there was only one pipe there, and the area would be 1/9 as much, then it would be 18 meters per second. By the way, 9 times the speed. And here it's only 4.5 times because it's split among two pipes. Sorry, talking a little too long about that. Okay, so now to find the pressure at either these location A and B, I'm going to use Bernoulli's equation again. These are looking down from a top view on these pipes. There is no change in height, so that cancels out for each term. We don't need to think of both pipes at this point because we already took that into account when we found the speed. So we're just going to plug in 50,000 here at point A, 1/2 rho v squared equals P2 plus 1/2 rho v squared at point B, end up getting 11,500 pascals. Problem 65 took me most of a page. So basically, I tried to draw a bunch of this stuff. I believe it was water, so yep, so that was 1,000 kilograms per cubic meter. And it's asking what the pressure is when this exits here. Well, if it exits into air, it's 101,300 pascals. So when it comes in here, it would be something different than that. This would be 101,300 pascals if this is a pipe open. And essentially, you're being asked to figure out the height of this standing column of water. So in order to do that, we need to find the pressure down at this point. So you're told the area here is 5 centimeters squared, area here is 10 centimeters squared. So if the area is double, the speed would be 1/2 as much using the continuity equation. I talk about that right here. Now we can think of Bernoulli's equation to find the pressure down at the bottom. So P1, we've said this several times. H here is going to be at 0 meters. H here is going to be at 4 meters. So I end up getting that the pressure at this location down here is 146,500 pascals. Now this column of water is still, it's not moving. But if the pressure here is 146,500 pascals, the pressure caused by this column of standing water plus the atmosphere should equal 146,500. So now I'm going to go back to this equation, which is pressure equals pressure of the atmosphere plus rho GH. And so I figured that this was the pressure at the bottom in the flowing part. So therefore that's got to be the pressure caused by this column of water. That's the atmospheric pressure, density of water, G, and finding the H. So this H is actually going to be 4.6 meters from here up to here. And so that's why this is actually a little bit taller than this pipe exits, which is kind of interesting. So that tells us that if this pipe had gone a little bit higher, we would not have fluid coming out of it. Anyhow, I hope those make sense, and thanks.